Hi guys, it's Mrs. Moss here. We're going to continue talking about the Earth's geological history, but this time we're going to talk about the absolute dating of rocks or fossils. So what is the difference between relative dating and absolute dating? Well, let's remember back to our previous screencasts. Relative dating uses rock strata to determine if a rock is older or younger than the other rock. That's known as relative dating because you're saying whether it's older or younger. Geologists use the laws of original horizontality and superposition, and they also correlate rock strata to determine the relative ages of rocks. Well, now we're going to look at absolute age. And the absolute age of a rock is the measure of how many years old an event has occurred or an organism lived. So instead of just saying a rock is older or younger than another one, we could actually say that this rock is 56,000 years old. We're going to give an age to this rock or fossil. And we use radioactive dating to determine the absolute age of a rock or fossil. Radioactivity is the ability of an element to change spontaneously into a different element by losing or gaining matter from the nucleus of the atom. We're going to look at our Earth Science reference table, first page, to help us with this process. So you're going to need to hit pause and get your reference table out. Radioactive decay is when a radioactive element, known as the parent element, changes spontaneously or decays. Because the nucleus is unstable, it will cause change over time. This will change into a daughter element, or we can call it decay into another element that is more stable. And it is the result of this spontaneous change. Let me show you a picture. In here we have the yellow isotope, which is the radioactive element or the parent of this daughter isotope. So in this picture, this yellow over time will decay or change into the daughter isotope. We call this the half-life. And this is the time it takes for half of a radioactive element to change into a decay element. So when we talk about half, we're literally talking about 50% of that parent changing into the daughter element. And that half-life allows us to see how much time has passed from one parent element to change into the daughter element. The rate of decay, or the half-life period of time, it's not affected by any outside conditions such as heat, pressure, or chemical actions. So that's what makes it so reliable to use to determine age of fossils or rocks that are so old. Now let's look at this chart on page 1 of the reference table. It's the half-lives or the radioactive decay data. And what you see is a list of the radioactive isotopes. These are the parent isotopes. And you see what they can change into. This chart in the middle shows us what it begins as and what it changes into. So at the right side of the arrows, these are all of the daughter isotopes, or the isotopes that it will change into over time. And this last column tells us the half-life, or the number of years that that parent isotope takes to break down 50% into the daughter element. And as you see, we have carbon up at the top. Carbon-14 has a short half-life, 5,700 years for it to decay to 50% of what it started. And therefore, we use it to date the remains of living things, such as bones, wood, and leather. And if we continue looking down this chart, uranium, on the other hand, uranium-238, it has a long half-life, 4.5 billion years. And so we use that to date very old rocks. Let's look at a sample practice problem of what we would use this radioactive decay data chart to help us solve. If we have a rock sample that contains 8 grams of potassium-40 when it was formed, but now it only contains 2 grams due to radioactive decay, what is the approximate age of this rock? Well, we're going to set up a T-chart to help us with this. One side of the chart is going to have time in years, and the other side will have the mass or the gram of the sample that's there. We're going to look at potassium 40 on our earth science reference table because that's what's given to us in the diagram. That's what's given to us in the word problem. And we're going to try to solve this and figure out how many half-lives this sample has gone through to get from 8 grams to 2 grams. And using our half-life chart, we can then see, once we know how many half-lives we have that it had undergone, we can then see the age of the rock. So let's go through this. Well, when we found the sample, it has first had 8 grams, right? After no years passed, there was 8 grams of the original sample. Well, after one half-life, or 1.3 billion years, there would be 50% of that 8 remaining. So therefore, we would have, after one half-life, we would have 4 grams of the sample left. But that's not what the question is asking us about. We have to get to 2 grams. So that means this sample would have had to gone through another half-life to go from 4 grams down to 2 grams. So if we look, this actually counted up 2 half-lives. We went through one half-life to get to 50%, which was 4, and another half-life to get to 2 grams, which is what we were looking for from our word problem. Once we have this and we know that it's gone through 2 half-lives, we add these half-lives up. So 1.3 billion years plus 1.3 billion years gives us 2.6 billion years. And that's the age of the rock. This rock is 2.6 billion years old. So that's how we use radioactive decay chart. We're going to do more practice with this when we get into class, but you're going to need to write this problem down in your notes. So write down the problem and what the answer is, and we'll go through it again next time we talk. Have a great day, and that's the end of our geological history, so I'll see you next time.